Hi, and welcome to one of my absolute favorite classes in this whole lecture series. We're going to talk about differentiation of measures and Vitali coverings. Now, before we get into that, I just want to mention that this part of the book is actually not that popular with some of my colleagues because there's a parallel theory here to establish the same major things, more or less, which is called maximal functions. And this book just completely ignores that topic, and I'm pretty sure it's in Stein's book. So if you really want to get to the depths of understanding integration theory and various alternatives, and these maximal functions are a bit more powerful than this what I'm going to present today with the Vitali coverings, but not as elegant. And it's the elegance which makes me like very much this argument here. So strap your seatbelts on, and here we go. Right, differentiation of measures in RD with respect to Lebesgue measure. Now, the theory is by no means more complicated in RD than it is on the real line. So we'll just stay on the real line, and in the book they do it in RD, so you can read there what appropriate modifications you need to do. So here we're going to talk about intervals in RD. That's a multi-cube. Basically, that's about it. So recall absolute continuity. If a measure mu is absolutely continuous with respect to lambda, which meant that if this gives 0 to a set, then this guy also should give 0 to the same set. If we have that, there exists by the Radon-Nikodym theorem a function f in L1 such that the mu is equal to f de lambda. Now, the question we ask here is how to recover f if we had the measure mu. And in particular, if you remember this guy, big F, right? We constructed a function related to every measure on the real line. We had a function that we got from integrating from minus infinity up to x, where x is a floating point. And it was important to include x because this measure mu as a singular part with atoms, points which give measure to a point, positive measure, not 0, then this is important. However, if we now assume that the measure is absolutely continuous, we can write this as just the integral of the Radon-Nikodym derivative. We call it derivative, so then it doesn't matter. I just use Riemann notation here. So this is called the Radon-Nikodym derivative, but in which sense is it the derivative? And most importantly, if we differentiate this big guy f, do we recover small f of x? Which we should in an intuitive sense, right? If f is C1, we know that this is true from the fundamental theorem of algebra. Yeah, so this difference here is just the integral. Here you put x, here you put x plus h. So it's somehow averaging f out in the neighborhood of the point x. So the question is like, how volatile is f in that little neighborhood, and how good is the point value at x as some sort of estimate of the average of f in that neighborhood between x and x plus h. Of course, h can also be negative, but we for the discussion we think about it as positive number. And, these functions can be discontinuous like hell, right? So when you start to think about it from that point of view, like maybe this shouldn't be true all that often, because for every point x, the function can be quite different. Here's f of x, and then here is what it's doing in a neighborhood. Then you take this point, and it's like, yeah, but it's somewhere. Function in the neighborhood can always be somewhere else, right? That's very little continuity. I mean, functions that's the whole point of the Lebesgue integral, right? To integrate functions that are not continuous at all, right? So we have no restriction, like in the Riemann integral, that the function has to be well behaved in any sense, right? Except for measurability, which is like super weak requirement. So armed with that, we can even ask the question, is this even something we can define properly? And if so, where? I'll keep you on hold, cliffhanger, before I tell you the answer to these exciting questions. So we have to introduce some boring notation. So this is like the upper derivative of the measure mu. So the Lebesgue here, we could write the u, the L, but the lambda, but that just got too many symbols. So d with a bar on top is the superior derivative. Let's see what that means. Yes, we fix a point x. Okay, maybe here is my x. Okay, up here still, this is just this is my function f, right? Here's my graph. My point was this one, right? And now I take an interval around this point whose length is less than delta. So I put some tap on how big I'm allowed to do this. But I don't see anything about, so you can slide back and forth, right? As long as it contains x. And then what we do is somehow we integrate over this piece of the function then, this, whatever it's doing here. We integrate over that and we divide with the length of the integral, right? So as in the traditional derivative, mu of I divided with lambda of I. So lambda of I, if I has length h, that's just h corresponding to this guy, right? U of I would be its difference if our measure is absolutely continuous. So we do that. We take a supremum over all such quotients with the restriction that the length is less than delta. So clearly, if delta now is smaller, I make it smaller, then I have a supremum over a smaller thing. So that's lower in value. So this will be a decreasing function of delta or non-increasing. Now, non-increasing things, we can take the limit. Yeah, the limit always exists. This is like the completeness axiom of the real line. So this lim sup here really exists. It gives you somehow, if this is the point, okay, so where was I here? Right, so you clearly want to put your interval here to as far to the left as possible, because it seems the function is like bigger over here. That's where you will get a maximum quotient. And then you take a limit, and maybe it's equal to, or maybe it's not equal to the value at the point. F of x could be like here, it is connected from the rest. And then, of course, we're going to do the same with the limit, and we're going to ask when are these two equal. If they are equal, we're in business. Or at the point where they're equal, we're in business. So now answers to your questions. Right, so the first part says, I have to look in the book. It says that the upper derivative and the lower derivative is equal at lambda almost every point, right? So this is surprising. This kind of says that this differentiation process I outlined above will work almost everywhere. All right. So since this holds almost everywhere, this guy and that guy identify the same equivalence class, right, as functions. We identify functions that are equal almost everywhere with the Lebesgue measure, then this and this is the same guy. So we need a notation for that, and clearly we're going to pick the just d without bar, neither up nor down. So d mu of x, we will define it as the superior derivative when it's equal to the inferior derivative, which is almost everywhere by this, and then 0 elsewhere. And now with that definition, we can now continue this theorem. I just bake everything into one bake. Right, this function we get is the randomly cordon derivative of the absolutely continuous part of mu. And this is completely mind-blowing, right? Because mu is a complicated measure, right? Potentially it has also a singular part that we know live on a set of measures 0. Clearly on that set, we're going to have a problem, you know, with the singular part, the set where the singular part lives. I don't think we'll get equality anywhere. I wouldn't sign on that, but I don't believe. So somehow that set will end up in the 0 measure set where this function is just identically 0. But everywhere else, more or less, we just get back that randomly cordon derivative of the absolutely continuous part. So this is the first time, I mean, randomly cordon is one of these millions of just abstract statements in mathematics telling you that something exists. Now we have a method of actually computing it, given mu, or approximating it at least. So with this, armed with this, before I get to the proof, let's do the corollary here. Right, it's hard to be more redneck than to spell Rolls-Royce wrong. We try to say that something is glamorous. But anyways, this is Sweden. It's a dump of a country. So, sorry about that rant. Fundamental theorem of analysis, the Rolls-Royce version reads as follows. Right, so if big F is just absolutely continuous, then we know that it has randomly cordon derivative. We established that in 4.4. But now we know that this df dx, as I defined it above, just standard limit. H can be positive and negative. It exists almost everywhere, and it gives you that randomly cordon derivative. So I just write f prime here. It means the same as this. It's just easier to write down. So then f of x is given by the value at the endpoint plus integrating the derivative between the endpoint and x. Just like in the fundamental theorem of analysis, but just so much more general and so much more elegant and perfect. Now, so to prove this, there's this key lemma, which seems completely harmless at first sight, but definitely isn't. I'll write up the lemma. Right. If we start with some Borel subset. Okay, so right. I'll paint it in 2D, although we're doing it in 1D here. But you know, so in 2D, as I said, the counterpart of intervals is like cubes, same side length, parallel sides with the axis, coordinate axis. Okay, so if you have some set where for every x in your set, so I take a point x here, and then this here means that basically, well, at least if I go, for every x, I can take, there exists some cube I such that mu of my cube I divided by lambda of my cube I. Since this is like a slim soup, I cannot say that this is bigger than or equal to A, but it's going to be bigger than or equal to A minus some epsilon, right? So you see here, you have what we want to establish, right? This is the same. If I divide this guy over here, and I just said bigger than or equal to A. So here I have that A minus epsilon. So I can do that for this point here, and then I can do it for this point here. Of course, if I now start to overlap, then I run into a problem if I want to generalize, like to say that this holds on all the cubes I. We usually call cube C, but now I stick to I. I comes from interval, right? If I want to say that this holds on all cubes I, then and then lift it to someone say that it holds on A, I'm not allowed to have some overlapping here, right? But let's suppose that we have some way, for some method of choice, we choose rectangles like this. And of course, or intervals or multi-cubes. Of course, they're allowed to stick outside. There is no requirement that they're inside. Yeah, if we keep filling up like this, at some point, you're going to fill, you have a covering of most of your A. So what you want, this is I1, this is your I2. You want, according to some rule, to get that A is a subset of an infinite union of these guys Ij. And then for each Ij, you have this, and then you play with these measures and yada yada. The computational rules for measures, and then your epsilon is fixed at arbitrary, and then you can kind of see that at the end of this argument, you get something like this. But here's the catch. How can I know that, I haven't specified my rule for choosing the I's. And how can I design a rule for choosing the I's so that I don't miss a big chunk of the original set A? Because actually, it's unclear if we can, by such a process, cover the whole of A. Maybe there will always be some point. I mean, imagine this. Okay, so we're back on the real line. So you take an interval here, right? And then at some later step in the process, you're forced to take this interval. Now, these intervals are open. Didn't I say that? Well, anyways, they should be open. Sorry, they should be closed. My bad, my bad. Closed ones, closed intervals. Right, okay, so then it's harder to. My point was that then this point here in the middle maybe is not chosen, and then you're not allowed to put an interval on top of it due to the requirement that they have to be disjoint. But we can easily see the same. Okay, so with closed intervals, we pick this one, and then, well, I don't know. But anyway, this can happen. So, okay, to realize that this is fishy, let's say we want to cover the whole real line, right? Then we can take a countable dense subset like the rationals, and for every rational point, we pick an interval I such that we have this. Yeah, that's our I1, and then we take the second rational point, If the rational point is already inside the I1, we of course move on. But sooner or later we find a rational point outside, and then we pick an interval there that covers I2. And like that, we end up covering all the rational points. But we wanted to cover the whole real line, but the rational points are dense, so somehow, yeah, we cover the real line as well, right? No. Go back to lecture 1 or lecture 2. We learned that you can cover, so the rational points there, Lebesgue measure 0, right? Which means that we can find such a covering that I just described, such that when you sum up the infinite amount of intervals, you get less than epsilon, where epsilon is arbitrary. Whereas, you know, so we miss basically 100% of the real line by doing this process. So, how can we come up with a clever selection strategy that we do not make this mistake? So that this is too much to aim for, okay? So what we want is not that A is a sub, because this, sorry, let me finish my sentences. What we want is not, or we would want that A is a subset of this, but we cannot get it. But what we need here in order to draw this conclusion is that this inclusion holds almost everywhere. We need to know that the set where we failed is ignorable, right? So you want basically, yeah, so we just scrap this. So A will be inside the infinite union. But the infinite union, that piece is outside, that's fine. What's not fine is if a big part of A is outside. So we look at A minus the infinite union of the ij's, and we want the Lebesgue measure of that to be 0. If we reach that goal, then we can prove stuff like this. And that is what Vitali coverings are about. So this brings us now, we're at the start of section 6.2. He just throws Vitali coverings out there without much talking about why, and then he comes to this stuff later, right? So I did a reverse journey here. All right, so a collection of sets which are closed intervals, or in the higher dimensional case, multi-cubes, is called a Vitali covering for a given set A if, and now comes for all x in A and for all delta bigger than 0, there exists an interval in my Vitali covering such that x is in the interval and the interval is not bigger than delta. Okay? So in this picture here, in the two-dimensional setting, let's say, okay, I can pick this one. And then I have a lot of smaller ones out here, but there are no small ones inside this one. And here's my point x. So yeah, I can cover, you know, a covering, we use that in topology all the time. It's just a bunch of sets so that every point x is inside at least one set in the covering. So the only additional ingredient here is this one, that okay, if my x is inside one of the boxes, that one has a finite size. But then there needs to exist a smaller box also. Given any delta, there should exist yet another smaller box. So each x is actually infinitely many boxes, and the length of these infinitely many boxes can go to 0. Yeah. That's what a Vitali covering is. Right, and now the Vitali covering theory. Right. Given a subset R and a Vitali covering V of that set A, there exists a disjoint sequence of sets ik instead of ij. I don't know why I changed this to a k. It just happened in the paper, so I decided to play it safe. Okay, 1, 2, 3, 4, 5. We enumerate a sequence of sets in this possibly uncountable amount of sets, or usually uncountable amount of sets, such that the infinite union here covers lambda almost every point in A, which is precisely this what I wrote here, right? Beautiful, nice theorem. And in the proof is where we need this like clever selection argument. So the Vitali covering is just this. It doesn't say anything about how you choose things. The proof, however, tells you how to pick things in a smart way. So I'll erase the blackboard and you think, how would I choose? You know, given A1, you pick your I1. How do you pick I2 and then I3 in order to not have too many gaps? Think of that, I erase, and then I'll show you how. All right, so the idea of how to pick the sets is actually pretty straightforward. Yeah, this is one of these things that you have to have tried to solve first in order to realize how smart it is, because it's not really the picking of the sets, it's just sewing the bag together at the end. Anyways, here's the argument. So first of all, we can suppose that A is a subset of some finite set, right? Because if we can do this, let's say, for whatever bounded set, then we can just do some limit argument. And you know, you're full, if you're in R2, you write here, and then you have a ring here, and then you have a ring here, and then you just prove what you want in every one of those rings, and then you add up the result and blah, blah. So we can assume that we're in some bounded set, and on the real line, we can just say that that bounded set is the interval between 0 and 1, so then it's a bit easier. Actually, I don't want the endpoints to be in A either, so I'm going to require this guy to be open. Yeah. As usual, I got it a bit wrong, or I forgot to mention a few things. So let's start over again. Okay, so we can assume this. And the first thing we're going to do is just throw away all the i's which are not subset of the interval 0 to 1. So here's your 0, here's your 1, this is your x. You know, this Vitali property says that, you know, no matter how small is your delta, you can always find a set I which covers it smaller than delta. So as long as delta is less than the distance to the boundary, you can always find one inside. So if V was a Vitali covering, V1 is going to be a Vitali covering as well. This is mainly to kick out very big. We don't want, you know, sets that, you know, size goes to infinity somehow, right? In our argument. Because now we can put delta 1 be equal to the supremum of the length of the intervals in our sub-covering V1. Yes? And now, just select any guy from here, such that, so okay. The selection process here is not really that clever. It's just the whole thing, like how you sew the bag together, that's clever, right? So what I'm gonna do, when I pick my first I1, I'm gonna pick it so that I'm not too far away from this value. Let's say we chop it off by half. Okay, so then I picked a concrete I1 here. Now, all the points, this was, you know, all the points under this guy are now covered. So I have to worry about the points of A, which are outside of that one. Now, since this is a closed interval, if I have a point outside, it has a finite distance to this guy. And so again, there must just pick a delta, which is less than this distance, and then you have a covering, a set that covers x, which is smaller than that delta. And then you see that, yeah, there must be some point here, I2, which covers this guy x. But the nice thing with how this intelligent selection process is, it's not like, okay, now let's figure out, like, we have to cover this piece and then that piece and blah, blah, blah. It's not that detailed. It's actually very simple how we choose the sets. So what we're going to do now is first we introduce V2, which is equal to right. So we're interested in the sets which have no intersection with the I1 we already chose. Yeah. So this is a very natural reaction or idea. And then this becomes then a Vitali covering of what's left, you know, of A without this guy I1. And then, similarly to this here, I'm doing now delta 2 equal to the supremum lambda of I such that I is in V2. And then I pick my I2 such that lambda of I2 is bigger than delta 2 divided by 2. So this means that, you know, maybe here this I2 was very small. Yeah, we have to avoid to not leave too big gaps. Maybe here's another x, which is covered by a much bigger guy. Yeah, and then this says that, well, if this is more than twice the length of him, I'm not allowed to pick that as my I2. He has to wait. Here's my I2. Yeah? And that's the selection process here. So I just write ...
Continue inductively.
So in particular, your nu3 is going to be equal to all the sets I in nu2 such that I intersect I2 is equal to the void set, right? So this being in V2 means I've already excluded intersection with I1. So if you want, you can just say, you know, I in your original guy, and then here you just list that the intersection with both, all the previous ones should be void. So this is just a requirement that every time you choose disjoint once. Okay, what do we have now? Well, each time, since these are disjoint, I have that the union A going from 1 to infinity, in my I case, well, it's a subset of the interval from 0 to 1, meaning that the infinite sum is less than or equal to 1, right? But each one of these is less than, well, it's larger than, wait a second, 2 times this. Okay, I can make this 2 times this. This is larger than, okay, then I get this. So this here is bigger than or equal to corresponding delta k, right? So now I get, in particular, that limit of these delta k's is equal to 0, or if they go to 0, the limit as k goes to infinity is 0. All right, so why do we then get this property that we covered almost every x? Why don't we, well, why can't there still be big holes here? Well, consider this guy here, x, and consider an interval that covers it. That was simply never selected. Yeah? So something like this. Here's the I that was never selected. But since the delta k's go to 0, it means that this I has to be kicked out at some point, because the supremum of the ones that remain is smaller and smaller all the time and go to 0. So there will be a point in the process, let's call it big K, when I is going to be thrown out. Right. So I is just a fixed guy that contains an x, which was left out when we did the infinite union. So in the this a set minus that we want to say that it has measure 0. And then at some point, I is kicked out. So it's going to be in the Vitali covering of the remainder. So x is always in the remainder, right? So I is in the Vitali covering here, but it's not in the Vitali covering over there. Right. This is so fucking beautiful. So let's say this, let me repaint here. So this is my I K. So what's wrong with this picture? Well, first of all, it's wrong that this is a very short one. Yeah, I K was supposed to be chosen to have a length at least half of the maximum length of what remains. So the length of I K is at least half of this guy. So it's a bit longer, but still maybe they don't intersect. Yeah, so this maybe something like this is okay. But now it's being kicked out in the next step, is no longer here. What happened when we went from here to here? Well, we just threw away all the intervals that intersected with the last one chosen, meaning that they will indeed overlap a little bit. Yeah? And now, since we know that they overlap, they are close to each other, And we know that the length of him is not that much. Actually, it's twice the length of that guy maximum. But if we just boost the length of this guy, so add twice on this side and twice on the other side. So take this guy, it has this length. Then you just do one more and another more here, and another one there, and another one there. Now you're certain that you've covered all of your I, right? Yeah. Because if you don't have that, again, your IK would be too short. This requires some thinking. And in higher dimension, also a bit more thinking. But I leave that up to you, at least from an intuitive point of view. If he's big enough and they intersect, and if you stretch him a bit bigger, then he will overlap completely. So this will mean, so let JK be the intervals with same center as IK, but 5 times the length. And now I make a claim then that, okay, so now we know that then my X here is inside of this guy, which I decided to call JK, right? But on the other hand, my X was just an arbitrary guy, which was not picked up in this union, this infinite union. So we have that the infinite yeah, here, God damn it, I like this argument. So I was about to say now, okay, I take the infinite union here, and that's bigger than or equal to my A set minus the infinite union, small k goes from 1 to infinity, IK, you know? So this is the one I want to say I measure 0. And then I want to kind of, well, yeah, but this doesn't tell me anything. This is a huge set here. So we have to be a bit more clever still. What I'm going to do is I'm going to cut this guy up there, okay? And then actually, if you analyze what I said, I get that every X which has not already been selected has to be in the remainder here. So let's take then, let's start this sum at, okay, now I have big K there, so let's call this J, oh, J is also bad. M. So M goes from K plus 1 to infinity. Now this is a true inclusion. Okay. So the Lebesgue measure of A set minus.
This is less than or equal to the Lebesgue measure of this guy's.
But this is less than or equal to M goes from 1 to infinity. And now we know that the length of this is, well, okay, so 5 times the corresponding length of your IMs. But this is a sum which is, you know, this sum converges. So I can always pick a K such that this is less than whatever given epsilon, right? And now, okay, so that just says that this is less than epsilon if I pick K big enough. Yeah, but now we have that, now we throw in this guy, the infinite union. He's a subset of that for every K. So here we have less than or equal to, you know, that. And now you see that the Lebesgue measure of this is less than any given epsilon. Epsilon is arbitrary. Boom. I mean, this argument gives me goosebumps. I think it's the most clever one in the entire book. And now I have to go and pick up my kids. So today's class is over, or at least I stop lecturing now. Maybe I continue tomorrow. I haven't made up my mind. Okay. Okay, so then let's do this key lemma that I mentioned earlier. So if I'll do it a bit more detailed now, if A is a subset of the Borel sigma algebra, and mu is a finite Borel measure, and A is inside of the set of point X such that the superior derivative of mu fx is bigger than or equal to A. So mind you, we still haven't shown that this set is actually measurable. So otherwise it would be natural to just talk about this set as a whole. But anyway, it's stronger like this, and we're going to prove in just a little while that this is indeed measurable. Then, so if we have all this, then it follows that mu of A is bigger than or equal to A times lambda of A. Okay. So the first thing to notice is that, okay, if we take an X, no, let's start with an epsilon as usual. And then you consider the collection of all the intervals I. All intervals such as this divided by that is bigger than A minus epsilon. Now, here there's no reference to A, but that doesn't matter because for every point X in A, we know that this big A, we know that this lim sup here is bigger than that A, which means that we can find an I arbitrarily small, or how small we want, such that this divided by that is bigger than A minus epsilon, right? So this is a Vitali covering of the set A, no matter what subset A is. Right, so then we use the Vitali covering theorem to pick a disjoint sequence ik of sets in our Vitali covering such that, no, I got it the wrong way, right? So A set minus this guy can be bigger, that's fine, but it should cover almost every point in A. So he goes here. Right. So now, and now we run into trouble, right? Because the next natural thing to write is mu of A bigger than or equal to mu of the infinite union. But this, I just said it, this guy can be much bigger, so we can't get that. Aha! This is the second time in a short while that we're going to have to use regularity. So I'm very happy about this. So this is a finite Borel measure in R or RD. So theorem 156 tells us that it is regular, meaning that this set here, mu of A, can be approximated arbitrarily well by an open set, which includes A, right? So, I write with yellow here. This goes in here. Let U bigger than A be such that mu of U is less than mu of A plus my epsilon, all right? And then here, I will require that my i's are subsets of the U, which doesn't change anything because U is open, right? And for X, a point in U, it has a finite distance to the boundary of U. So since this is a Vitali cover and these i's are as small as we want, there's always an I small enough so that's already inside the U for a fixed X. So with this addition, it's still a Vitali covering of A. And now here, this infinite union automatically becomes a subset of U, right? Because each one of them is a subset of U. And now this is mu of A plus epsilon is bigger than that. And see how beautiful this becomes. Now the rest is kind of clear how the argument goes, right? So here's the infinite sum. And then we use the inequality that defines these things. I use less than or equal to everywhere, doesn't matter. Now the sum goes back inside. These are disjoint, so I have identity. And now the Lebesgue measure of A set minus this has measure 0, right? So if I add whatever was in A, I just add a set of measure 0, so that's fine, right? And now this is bigger than A. Ta-ta! Now epsilon is arbitrary, so we let it go to 0. And if you look at the left-hand side and the right-hand side, we have established precisely this equality. Beautiful, no? We will also need the corresponding statement when you have the inferior derivative, and then this inequality goes the other way. And usually, you know, it's like proposition 125 and 126. Every time you have something going one way, there's for a sup there's for an increasing sequence, there's a decreasing sequence statement, and they're usually very similar. Here they're actually not. So okay, so what's different here? This inequality, this is the inferior derivative. The rest is exactly the same, but look at this assumption here. Mu has to be absolutely continuous with respect to lambda. And that is because, so, you know, when I came here, I didn't have that guy. And then I said, well, I can throw him in, it doesn't matter because the Lebesgue measure of A set minus this is 0. That's what the Vitali covering tells us. When I do this argument here, which kind of will go the wrong way around, right? I'll have my lambda over here and my mu in this side. I will need to know that mu of the corresponding thing A set minus this has 0 measure, but I don't know that. I know that lambda of that thing has 0 measure. So that's where absolute continuity comes in, right? Because that's exactly what absolute continuity says. It says that if something has 0 measure here, the measure is also 0 under mu. Right. So armed with that, the details are a bit almost the same. Lambda of A plus some epsilon is bigger than lambda of U. So I skipped these 2 lines. They're identical with the change that here I'm also working with lambda. Now I use the regularity of lambda, not the regularity of mu. Why? Because I just want to copy paste this computation here, and then it is lambda I need to approximate with an open set in the first inequality here. And then we just go, this is less than or equal to lambda, the union k of 1 to infinity ik equal to sum less than or equal to, okay, sum lambda ik, I'll write out everything. And then we had, okay, a plus epsilon mu ik, right? No, not right, you stupid git. Now the a plus epsilon is on the wrong side of the equation, you dumb punk. I get so tired of this. I'm a living proof, I usually say, and it really is, I'm a living proof that if you just try hard enough in life, you can become anything you want. Really, talent is subordinate to effort. Anyways, the a plus epsilon is on the wrong side of the equation, and it's an easy fix to just do a -1 up there, and then the computation works out. I have no feeling. There's a very strong wind. I don't want to back to the university and redo this shit, so I'll just post-fix it, okay? And follow my example and work hard, and you will make your dreams come true. So, I should have said that too, maybe, but you know, you have to work out yourself a bit which things you should change. So I said these two lines are exactly the same. Of course, this inequality has to flip, and when it does, we also need to put a plus epsilon here to know that we get that there exist sets that satisfies this. Yeah, because the inferior derivative is less than a. It means that for a plus epsilon, if you go a bit above, you can find a set such that this divided by that is less than, because we work with an inf, not a sup. So that's why I have a plus epsilon there. And now, right? This is what I get. And what I want to do is I want to add this guy and claim that he is 0. But I cannot, because the Vitali covering tells me the Lebesgue measure is 0. So, armed with absolute continuity of mu, this statement is true. So I throw these together, and all in all, this is bigger than or equal to just, so I can put a parenthesis here, right? And then I get a plus epsilon mu of a. And now epsilon is arbitrary, yada yada. Proof is complete. Okay, I think that's good enough for today. So next time we'll finish chapter 6. So in particular, we'll do this beautiful theorem that in RD, the derivative defined as a set of points where the superior derivative and inferior derivative equal, that is the same almost everywhere, equals the Radon-Nikodym derivative, and also then finish up. There's a whole chapter with exciting applications to just differentiability of functions on the real line. So I will do a selection of that. But in particular, we will do this fundamental theorem of algebra, fundamental theorem of analysis, Rolls-Royce version. So see you next time, and thank you for today.